Hi, my name is Mayank Sharma, and this is my submission for the second trial of video assessment for the enterm of the subject code Mat 104. So, yeah, that's all. So, yeah, let's jump straight into the problem. So, what I'm going to have is a bookish approach to this particular problem. So, in the book, what they have done is derive the Laplace transform for sine of omega t and cos of omega t, and I am going to do the same for sine of 2t and cos of 2t, and eventually derive for sine of 2t, which is a requirement of the given problem. So first thing first, let's write the expression for the Laplace transform of sine of 2t, which would be definite integral with limit 0 to infinity of e raised to power minus st times sine of 2t, which is our f of t here, and derived with respect to t. Similar for Laplace transform of cos of 2t, which would be definite integral of e raised to power minus st of cos 2t, and the the integral would be with respect to t. Let's, for the sake of simplicity, write the Laplace transform of sine of 2t as ls, and similar for Laplace transform of cos of 2t as lc. So first thing first, let's derive the expression for Laplace transform of sine of 2t, which would be ls. It is definitely, as we wrote already, let's write it again, and solve it with integral by parts. Here e raised to power minus st is our v, in case of, like, as you know, integral of uv with respect to, say, dt only. Here it would be u v dt, v dt would be integral, and then du by dt times integral v dt, and this whole expression then would be integrated. So this particular expression right here would be now equal to sine of 2t times integral e raised to power minus st, and the limits would be applied here, minus integral, this is the whole integral which is here, and this would be derivative of sine of 2t times integral e raised to power minus st dt, no limits here, this whole expression then would be integrated with respect to t, and yeah, let's solve for it. This would be sine of 2t upon s e raised to power times e raised to power st with a minus sign, integrating this, and limit apply, and this particular expression would be solved from 0 to infinity. Though solving to infinity is kind of weird, we are not supposed to put infinity directly, so we would be using limits, but that's for the latest steps. Let's focus on our problem currently here. This expression would change to derivative of sine of 2t cos 2t, positive here, e raised to power minus st integrated, then it would be minus 1 upon s, and minus plus 1 upon s here, that is, so this particular expression here would be e raised to power minus st times cos 2t dt. And if you see this expression right here, this particular one seems pretty similar, and yeah, you have seen it right here, and that is LC, the Laplace transform of cos of 2t. So yeah, let's write it. First thing first, let's write let's write first thing first, take this minus sign out. Limit a tends to infinity, cos we are not going to write infinity straight up in place of t because it does not make sense. Like, we don't know infinity. I mean, though we are writing it and limiting it, but it does not make sense writing infinity directly. So what we're going to do is a tends to infinity and replace t with a, seas, minus, if we put t equals 0, this would be s and this would be 0, so it's going to be 0, and it is 1 upon s Laplace c L of LC, that's what we're going to write. And let me take, I have derived this particular expression right here using maxima, though we can use L'Hospital's rule and other things too, but since I thought that we have tools that can help us out, so I have done that already. So let me head you straight to this my laptop screen. So yeah, and here I have evaluated the expression. Here you can see it is 0. If you can see, yeah, it is 0. It's not out of focus, right? Okay, so yeah, I have done same for cos of 2t, cos we are going to require this particular expression too soon in the derivation of next expression. Here, let's get back to the problem. So as we have seen, this is evaluated to 0. So basically what we have got here is L s equals 1 upon s LC. Let's denote it as equation 1. And here now it's time to derive LC, that is e raised to power minus st 0 to infinity of times cos 2t, and this would be integrated with respect to t. And same process, redundant here. Once again, we are going to write it, but here's the thing, the expression is going to be a bit different here. I'm going to write this particular integral directly here, cause yeah, it's going to be same anyway. What is point of writing it again and again? So s e raised to power st, yeah, let's write the expression here, evaluated from 0 to infinity, minus integrated from 0 to infinity d derivative with respect to t of cos of 2t times integral e raised to power minus st dt, no limits here, whole expression integrated with limit 0 to infinity dt. As you might have seen in the previous screen, previously that I have, when I share the screen of my laptop where I derived the expression, that cos of 2t, let's write it again. Limit a tends to infinity cos 2a upon seas, and when it tends to infinity, I have derived it already, it's going to be 0, minus, but when we are going to put t equals 0, we are going to get minus 1 upon s. I see, yep, we are going to get minus 1 upon s. No, wait, give me a sec. Yeah, we are going to get 1 upon s. I've already took out minus sign. So yeah, and minus integral 0 to infinity, it's going to be minus 1 upon s, but derivative okay, let's write it anyway. Sine of 2t minus se e raised by sg dt, this both minus and minus, I mean it's minus 1 and minus 1, so yeah, whatever. Let's get parallel, give me a sec. So the expression we get here is for Laplace of c, it's going to be 1 upon s, as you can see, minus times minus is plus, anyway, minus 1 upon s times integral limiting, definite integral limiting from 0 to infinity, e raised to power minus sg times sine of 2t dt. This expression is ls, so we get lc equals 1 upon s minus 1 upon s times s. So what I have done is that I forget to put 2 here. After deriving, we are going to get 2 also, so it's going to be 2 here. It was a silly mistake, could have costed me a lot of time, though it costed me about 30 seconds though. So yeah, it's going to be 2s. As you can see from equation 1, we do already know that LC equals S times LS, and I have also forget to put 2 here in the first equation too, so again a silly mistake. So we do know that LS equals 2 upon S times LC, so we are going to replace LC with S upon 2 times LS. This particular expression we have got it from the first equation, that is going to be 1 upon S times 2 upon S LS. Taking LS common, we are going to get 2s upon s square plus 4 equals 1 upon s, implies ls equals 2 upon s square plus 4, and this is the answer we were looking forward to. So yeah, that's all.